Good evening. Were you guys aware that there was not a session on 29th also? 30th, whatever that date was? 29th, sorry. Were you aware about that? Mandlik, Aparna? Can you hear me?
Yes, sir, you told that it will be on first, so
So it was clear, right? Take it. Okay, we'll wait for a couple of minutes and then we'll start. In the meantime, if you have any doubts from previous sessions, you can ask. We'll wait for 2 more minutes and then I'll begin with today's session. So that's all. Is my screen visible? Please confirm. Is my screen visible?
yes.
Okay. So thank you for joining. Just for starters, this will be the last session for this phase, NPTEL for the second phase. So today will be the last session from me, and I think other scholars may have already finished with these sessions. So that's that. But I might take, even though it's not with NPTEL, I might take one more session on the coming Sunday, that is, just to see if there is demand. But since only 2 people are here, so you feel free to ask any doubts that you have, since I can give you much better attention and try to solve your doubts. So my name is Amit. I'm a PhD scholar at Indian Institute of Science. We are discussing the physics previous year questions hosted by NPTEL, and this is a combined session for week 9 and 10 on February 1st, 2023. Right, last class we were talking about Schmitt trigger, which the question was incomplete to say the least. So just a quick overview of what an operation amplifier is. An operation amplifier is made up of 2 words. So operations, which operations are we talking about? We are talking about some basic mathematical operations like comparison, which greater than, less than. So greater than, less than, or equal to. These are very basic comparisons. Integration, it's you integrate signal usually from voltage from a given 0 time to, let's say, some time t. You can differentiate using an operational amplifier, and you can also perform the addition or subtraction. Why amplifier? Because it amplifies the input voltage. We'll see in a minute that what do we mean exactly, where the input voltage is and how to get the output voltage. And it is to be noted that the operation amplifier is subclass of differential amplifier. So differential amplifier is, as you can see on the left of your screen, on the bottom left of your screen. So this is a differential amplifier. You have given a power supply VCC and a power supply VEE, and these are the two inputs, V in plus and V in minus. Two BJTs which are identical, Q1 and Q2, and these are the resistors, and we are taking the output in this form over here, the difference between the collector voltages of these two BJTs. And if you do some mathematics on this, the expression of V out can be written in this form. Now it is to be noted that there are two terms here of importance to us. One is this AD term, the other is this AC term. And the AD term is known as differential gain, while the AC term is known as the common mode gain. So this is a differential amplifier. Now, how to convert a differential amplifier to an operational amplifier? We need to make sure of two things. One is that AD, the differential mode gain, should be much higher than the common mode gain. So effectively this term will be neglected, the second term will be neglected, only the first term will remain. And second is that the circuit has to be designed in such a manner that it will have a lower output impedance and a high input impedance. And this is a symbolic representation of the same differential amplifier, but when you apply these changes in your design itself. So V plus is the positive input, V negative is a negative input. Negative is also known as the inverting terminal or the inverting input. This is called the non-inverting. And as you can see over here again, that Vs plus is nothing but corresponding to Vcc over here, Vs minus is Vee, and we are taking the V out. This is the V out over here. This is a better model of the ideal operation amplifier, where you can see V plus and V minus, and the saturation voltages are given here, and this is the output voltage, and these are the typical terms that you will come across, and I've summarized them over here. So open loop gain is usually denoted by G or AOL. Ideal value is infinite, but really you get 10 to the power 5. Output voltage similarly will be saturated at Vsat. Input impedance is usually mega ohms. Output impedance is fairly low in ohms. Slew rate is how fast is your circuit switching, like from 0 to high to low and low to high and so on. The slope is what is known as the slew rate. CMRR, I told you what AD should be greater than AC. So when you represent it in terms of decibels, so 20 log AD over AC, this is CMRR. This is usually 6200. This means AD is 3 to 5 orders of magnitude higher than AC, and this is a good CMRR. And there is another representation, the same thing which you have seen earlier, and you can clearly see the output voltage expression clearly follows the expression from the differential amplifier. And this is a typical example where we are comparing two voltages. So when V in, you see this is the input, we are applying the input voltage to a positive terminal, non-inverting terminal, and the reference voltage is over here. So when the input voltage crosses the reference voltage, the output swings from low to high. It goes from minus VCC to plus VCC. This is a comparator circuit, and this is the same circuit that we'll utilize today to understand Schmitt trigger. But we also provide feedbacks. So there are two feedbacks, negative and positive. If the output node is connected to inverting terminal by some resistor, capacitor, any other circuitry for that matter, it's a negative feedback. It provides a stabler output, and examples are integrator and differentiator. Similarly, if the output node you see over here is connected to the positive terminal, the non-inverting terminal, using some resistor, capacitor, diode, whatnot, it's a positive feedback. It usually gives an unstable input, but we can still utilize them to create oscillator circuits or Schmitt triggers, which we are going to see in a while. So this is a circuit that we had. You can see in the question the circuit diagram. So what we have over here is this op amp, and input is given over the inverting terminal, and we need to find the waveform for the output voltage for the given input voltage, the triangular input voltage waveform, right? And so before we solve this question, there are some pre-checks that we should do. What is that? Is the op amp ideal or not? Because remember, all the expressions that AD equal to AOL VD plus minus VD minus and everything else is applicable only when the op amp is ideal. So here the question is silent about it, so we'll simply assume that it is ideal. We'll assume that it is ideal, so we'll assume that. ideal assumption. Secondly, we check what is the nature, if there any feedback is present or not. So we can clearly see the output voltage, the output node over here is talking to the input terminal, the positive terminal via this 4K resistor, and hence there is a feedback. So yes, there is a feedback. What kind of feedback? It's a positive feedback. Finally, we talk about this condition called the virtual short. So if we go to the previous slide over here, you see this, that there's a Rin over here, and Rin usually we can see that the input impedance is usually very high. So I'm going to utilize this thing over here, right? So what is virtual short? So this terminal is V plus, this is V minus. So what I'm going to do, let's say there's a resistor over here, Rin, right? And let's say there is a current I plus that is flowing in. So whatever I plus is flowing, it should be flowing out here also. So I can write the Ohm's law across this resistor. So I can write I plus times Rin should be equal to V plus minus V minus, simple Ohm's law. If Rin, ideally we assume Rin to be infinity, right? So what's going to happen is that these two are going to be shorted. They are going to be at the same potential, right? So no current will flow, so this will be 0. So we can say V plus minus V minus is equal to 0. This means V plus equal to V minus. Now V plus is this node, and V minus is this node. I'll use a different pen to illustrate the point. So V plus is this node, V minus is this node. They're sitting at the same potential. This means that's why they're called short. Why virtual? Because there's no actual wire shorting them. It's just the nature of op-amp is that because there cannot be any input current. So these two voltages have to be at the same potential. These two nodes have to be at the same potential. That's what we mean by virtual short. And this is a very important this is a very important property of an ideal operational amplifier. Excuse me. Yeah, so that's that. So we'll utilize this property over here, right? So now we come back to the circuit that we were given. So this is the circuit that we were given, and if you closely notice that we need to find the correct output waveform, but at time equal to 0, all the output voltages are plus 10 volts. You can see in all the 4 options, right? So what I'll say is that at t equal to 0, V out is plus 10 volts. Note, plus 10 volts is the saturation. Okay, so now let's just first try to evaluate what is the potential here at t equal to 0. Just let's try to evaluate. Let's call this node voltage V plus. So at t equal to 0, now note this is a potential divider, right? So I can write V plus is equal to V out minus 0. The whole, note that no current will flow here. So no current will flow here. Similarly, no current can flow here, right? So V out minus 0, this is the total. So all the current that is flowing over here will flow over this. So this is essentially a potential divider, right? So I can write V out minus 0 times 1K over 1K plus 4K. This is simply the expression for a potential divider. So this comes out to be V out into 1 over 5. V out is plus 10 volts at t equal to 0. So I can write V plus at 0, t equal to 0 is coming out to be 10 by 5 equal to plus 2 volts, right? So at t time equal to 0, this node is sitting at plus 2 volts. Now at t equal to 0, we start applying an input triangular waveform. So input waveform will start from here. So what will happen is that this op-amp will behave like a comparator. So this voltage, this node is sitting at, I'm writing it in different color just to illustrate. So what's going to happen is that, so case 1, when V in is less than plus 2 volts, right? This means in this part, in the purple region over here. So V in is less than plus 2 volts, and we know that. So V plus is sitting at plus 2 volts. Since the negative terminal is at a lower potential than the positive terminal, the output will be high, plus V sat. So I'll write, since V minus is less than V plus, V output should be equal to plus V sat, just like we saw in the comparator circuit. So what is V sat? V sat is plus 10 volts. So we can say that during this region, V output will continue to be plus 10 volts. So this is the first thing. Now what we'll do, now we'll take the second case, which I'm writing in green now. So let's consider the case when, case 2, what will happen when V in exceeds plus 2 volts, right? What will happen in this case? This means I'm talking about, let's say, this region and onwards. I don't know till what time, but onwards. So V plus again here at this instant, just at this junction, right? V plus will be plus 2 volts again, right? Because the potential divider remains the same. So now we can see, now since V minus is greater than V plus, this means the negative terminal, the negative input is at a higher potential as compared to the positive terminal. Now V out will swing to minus V sat. So V out will swing to minus V sat. This means V out will swing to minus 10 volts. So this means at this junction, so I'll draw the output waveform here itself so that it's easier to understand. So this is the output waveform. This was the region over here, and for the first part, the purple part, the output voltage we saw was plus 10 volts. So this is plus 10. Okay, now what's going to happen is that as soon as V in crosses plus 2 volts, this means at this point, what will happen? The saturation voltage will drop to minus 10 volts. So this is minus 10. This is the output waveform that I'm drawing, right? So what will happen is that now Vset has become minus 10, right? So now let's quickly evaluate. So if Vset has become minus 10 again, so at this, let's call this T equal to T1. So now at T equal to T1, what will happen is V plus, again the same potential divider, it will become minus 10 into 1 by 5, it will become minus 2 volts. So V plus now value will become minus 2 volts. So this junction will now be at minus 2 volts from this point onwards, right? So I'll just be more clear. This is V output. This waveform is for V out. And now I'm going to try a third waveform, which is nothing but V plus, right? So we saw that V plus for this part was plus 2 volts. This was plus 2 volts, and then at this junction, as soon as V in at this junction, it became minus 2 volts. So this is what we saw earlier, right? So what's going to happen now is that this case will continue to be the same. Now the comparator will kick in again when the reference voltage touches the when the input voltage touches the reference voltage. Now reference voltage is minus 2. So now we need to identify when does the input voltage now cross the reference voltage. So you can see the input voltage is now, when the input voltage will cross the minus 2 volts. Now the reference voltage is minus 2. So the input voltage crosses minus 2 at this junction. That's called T equal to T2. So at T equal to T2, this is case 3. When V in will become less than the reference voltage, which is now minus 2 volts, because V plus now at this junction is minus 2 volts. Now we can write, since V minus is less than V plus, now again comparator circuit will kick in. The positive terminal has a higher potential as compared to the negative terminal. So V out will again become plus V sat. This means plus 10 volts. So what's going to happen is that at this junction, it's again going to rise to plus 10 volts. And similarly, correspondingly, V plus will also rise to plus 2 volts, because V plus we know is given as a potential divider over here. So now I'll just complete the green curve which was missing. So it will be like this, and it will be like this. Now what will happen is that again in the next cycle, when again this time will come, so this will remain high. Now again when this time comes over here, right? So when this comes, so this will continue to be like this, and then when this time comes, when again the input voltage crosses the plus 2 volts, because now that is the reference, so the circuit will again switch, as I'm denoting in green. So this will again switch to like this, correspondingly this will again switch, and then this cycle will continue. So you can clearly see we have converted a triangular waveform into a square waveform. The voltage limits are accordingly decided by the plus Vsat and minus Vsat, because this is the output voltage cannot be arbitrarily high. It has to be clamped to these saturation voltages. So this is what is happening. So the key thing to note here is that the reference voltage changes It's not that the reference voltage remains constant in minus 2 volts or plus 2 volts throughout. When it's rising, when the input voltage is rising, the corresponding reference voltage was this plus 2 volts, you can see over here. However, on the falling edge, the reference voltage was minus 2 volts, and so the trigger points were different. This is sometimes also referred to as hysteresis, because the rising edge and the falling edge have different threshold voltages. So you should keep into mind, because there are different forms of this question usually that are asked. So you may want to just recall that the threshold voltages are different, and there's different terms that are used. Some hysteresis, that hysteresis is also, this word is also used, sorry, hysteresis, this word is also used, multiple thresholds. There are different phrases which are associated with a Schmitt trigger. And of course we saw this is possible because it's a positive feedback circuit, unstable circuit, and hence it oscillates. You can see that it's oscillating over here. Now we'll come back to the solution, the options. So we saw that the first trigger was at plus 2 volts over here, and the second trigger was at minus 2 volts, and then again at plus 2 volts, and then again at minus 2 volts. So we'll see that. So you can see this is falling at plus 2 volts, which we expected, rising at minus 2, which we saw in our waveform earlier, again falling at plus 2, rising at minus 2. So this seems to be the correct option, but let's check the other options. So we must see that the edges will be at plus 2 and minus 2. So you can see the edge is not there, so this is the wrong answer. Similarly at plus 2 and minus 2, the rising edge of plus 2. So you can see this is falling at plus 2, but again this is rising not at plus, this is again rising at plus 2, but it should rise as minus 2. It should rise over here like this option. This is also incorrect. Similarly this point, this means you have to consider this line, and then again this line, and then this line. So you can see that these two lines are matching, but this one and this one are not. This is also incorrect. So option A is the correct one over here. I'll again pause a bit and just summarize that what we had talked about. So we had taken this to be an ideal op amp, and we saw that this is a positive feedback. And if you are familiar, this is a typical circuit of Schmitt trigger. There are two concepts that are involved here. One was the potential divider. So this is over in this part, you can see this is the potential divider over here. So first thing, we need to know how a potential divider works. Second thing was I'll change the pen again. Second thing was over here, a comparator circuit. So these were the two concepts that were involved here, potential divider and comparator. These are the two electronic systems, you can see. And we saw that the triggers are different. So on rising edge it was plus 2, falling edge it was minus 2, and correspondingly the output waveform gave us a rectangular waveform or a square waveform, but the triggers were different. This is also known as hysteresis in case of a Schmitt trigger. So I'll pause over here for your comments or questions. You want me to repeat anything, please ask. Feel free to ask. You want me to repeat something that I've quickly went through, just I'll pause here for a bit and ask for your comments or questions. You can ask. Yeah, there are only 3 people in this class, so I can even very what should I say, intricately address your doubts. So feel free to ask. All right. If there are no comments, I'll move forward for the next question that we have for today. So this is a very straightforward question. Okay, I should ask this first. So how many of you have, of the 3 of you, all 3 have you a physics background?
No.
Yes, sir.
Okay, 1 no, 1 yes. Ashutosh? Okay, I'll assume it's a no, so that I'll keep the level accordingly. Okay, so have you read about capacitor charging and discharging?
Yes, sir.
Okay. Aparna?
Yes, sir.
Okay.
Yes, sir.
Okay, so this question is about, it's a very simple question. This is about charging of a capacitor. So I'll read the question from this is a fairly old question from 2010, but it often happens that the questions are repeated in gate or not in gate, like some question from just you change the wording and it appears in gate and vice versa. So the question says the figure shows a constant current source. We'll talk about current source in a while. It's charging a capacitor that is initially uncharged. So initially, so we can say that Q0, this means charge at time 0 is equal to 0. It's initially uncharged. It says when the switch is closed at t equal to 0, at t equal to 0 we close this switch at t equal to 0. Equation of the following plot denotes correctly the output voltage of circuit as a function of time. So we need to find V out, what is the waveform as a function of time. Okay, sorry, not a waveform, V out as a function of time. So we are required to find this, right? But first let's look at this term, what is constant current source. So what is this? What are current sources? So on the screen you can see two current sources. One is ideal current source, one is a practical current source. On the left is an ideal current source. So what it happens is that inside this current source is nothing but this the black rectangle that you see. So what it does is that, so ideal current source promises that I will output, so this you can see this infinite resistance over here, right? So no current can flow through here. So I call this I internal. I internal has to be 0 because it's infinite resistance. So I out has to be equal to IS if you apply KCL over here. So whatever current is being provided, whatever this current source claims, no current is lost inside the current source itself. All of it is output to the load. So we are applying some load here. Let's assume it's a resistive load. It can be a capacitor, it can be anything, but for the simplicity let's assume. So RL, so the current that is being supplied to RL will exactly be equal to IS. Now let's analyze the same situation over here. Let's apply the same load RL over here. Okay, yeah. So again, the practical current source says that I'll again supply, it promises to supply IS. Let's hold on a second. Okay, fine. So it promises to supply IS. So let's say how, but you see there is a resistor here also, RP, shunt resistance. So what will happen is that some current will flow here. Let's call this again I internal, and here this, let's call this current as I out. So if I apply KCL over here on this node, so it will be incoming current, that is IS, is equal to the outgoing current. Outgoing current is I internal plus I out, the current which is flowing through the resistor. Now note that it is only this current that is of importance to us, not other currents. Just a second. Yeah, it is only the current that is being supplied to the load that is of importance, because that's the whole job of a current source, to provide some current. But if some current is being lost, so you can, I'll rearrange the terms. So I out will be IS minus I internal. So if some current is lost inside, this means this source, practical current source, is not as efficient as compared to ideal current source. Now there are some 10 formula you can, for instance, derive the power that is out here in this case, and you can also derive the power in ideal case. And there are some ideality factors, eta ideality factor. I have a video on this in on my YouTube channel. You can refer to that if you are interested. But the summary here is that the practical current source has some inefficiencies associated with it. That's the whole idea over here. Okay, so now what we'll do is that now we'll take this picture and we'll assume it's an ideal current source, because question is silent about it. I'll assume it's an ideal current source. So whatever current is, so let's say it supplies current I. So there is no drop over here. So all the current will be supplied to this capacitor itself. Okay. Now what we are going to do is that now we need to find the output voltage across this capacitor C. So let's try to do that now. So how to do that? We know that that Q equal to CV. This is the famous expression for a capacitor. Q is the charge stored on the plates, C is the capacitance, and V is the voltage, right? So what I'll do is that I'll differentiate with respect to time on both sides. So I can write dq over dt equal to d over dt of CV. C is a constant, we'll assume C is a constant, so that will come out to be dV over dt. Now this V is nothing but the voltage across the capacitor. So I can write d by dt, this is nothing but V out minus 0. I'll write V out minus 0. Okay, so dq by dt is nothing but the current flowing through the capacitor, which is I. So I can write I equal to C dV out over dt. And what I'll do, I'll rearrange the terms. I'll take dV out to the left side. So what will it will be? It will become I over C dt. This is the expression, the differential equation that we had obtained. Now note that I is a constant because we are given this is a constant current source, an ideal constant current source. So I is a constant, C is a constant we have assumed. So if I integrate it, so from 0 to V out, kindly note that initially it's given, initially capacitor was uncharged. Initially capacitor was uncharged. This implies Q0 was 0, or we can say that V out 0 at time t equal to 0 was 0. So hence the lower limit is 0. Similarly, at time t equal to 0, output voltage was 0, and this is to a certain time t. So if I integrate it, it will come out to be V out minus 0 equal to I by C times t minus 0. This will come out to be V out equal to I by C over t. Now what I'll do is that so we have obtained V out is nothing but I by C times t. I is a constant because it's a constant current source. C is a constant we have assumed. So this is coming out to be Y equal to mx. Y equal to mx. This should be the expression. This should be the, and we have to simply plot this expression. So you can clearly see option D matches it closely. That's fine, but what's happening over here? Y equal to mx extends to infinity. It should actually go on like this, but there cannot be any in practical scenarios there cannot be infinite currents, infinite charge buildup. What will happen is that if you increase it to after a certain amount, either this capacitor will blow up, also there's a even maybe even before that, this is a current source, right? Usually these current sources are BJTs, depending on what the current is, but let's assume it's a BJT circuit that's providing this whatever the value of current is, right? Every BJT is driven by some voltages, VCC, VEE. So you cannot exceed a certain rated voltage, whatever that voltage V, it doesn't matter, but it will saturate at some certain point of time. The reason is that either the capacitor will just simply blow up, or the current source will hit its compliance. Well, it's rated, not compliance, it's rated voltage, whatever VCC or VE, whatever it is, it will hit some voltage. It cannot provide current endlessly. So that's what's going to happen. So ultimately this will saturate at some level. Which level, that information is not available, but we can be certain that it will saturate at some level. So hence option D will be correct. It will rise as Y equal to mx, a straight line, but after that it will saturate. So this is the key here, the saturation part. So yeah, so I have now finished the question. I'll again pause for a bit and let you just absorb this. If you have any questions, please ask me. I'll wait for a minute or two.
Sir, that saturation level,
yeah, you need me to explain it again?
That part, it's not clear.
Okay, so what's going to happen is that what we obtained was that the expression should be Y equal to mx. This is a straight line expression, and we so I'll write it again. Okay, so we obtained Y equal to mx. So what's going to happen is that this should be the answer, actually, the dotted line, the red dotted line that you see. Y, this is a straight line. But that's not going to happen. It's not going to happen because what this means is that there can be infinite amount of voltage that this capacitor can store, and we know Q equal to CV, right? So if you keep on increasing the voltage, this means you keep on increasing Q over and over, right? That's not possible because this capacitor it has some physical limitation below which above which it cannot perform optimally. So that's one way of saying it. The other way of saying it is that you can look at the current source over here. The current source over here. So these also operate at some voltage. You see that this node voltage will keep on increasing, right? So what happens is that all these current sources, which you'll see in a question today itself, so these current sources cannot operate above a certain voltage, because this current source is usually being driven by a BJT, bipolar junction transistor circuit, and every bipolar junction transistor circuit has some voltages which are provided to collector. Let's say VCC, we note it by VCC. So whatever the voltage, so the voltage across this current source cannot be arbitrarily high. That's my point. So it cannot be arbitrarily high, because then either the whole circuit will start to malfunction, or this capacitor will blow up. Whatever be the reason, there will be a point at which the output voltage should saturate. That reason can be the capacitor or the current source or the combination of both, but it has to saturate. It cannot sustain in an infinite amount of voltage, or you can say it cannot store an infinite amount of charge. If this were possible, a very small, your phone batteries will last for centuries, if this were possible. That's not the case. That's not a practical case. So that's what I mean by that, it will saturate.
Clear, sir.
Okay, thank you. So what I'll do is that I'll now move on to the next question. Right, so I just touched upon the BJTs over here. So this is a question from like 10-12 years ago. The question asks, which of the following statements is correct for a common emitter amplifier circuit? So I'll talk about these terms in more detail. Common emitter amplifier, what does it mean? How to not design it, but how does it look? What are some key features of this amplifier circuit? And we have to identify the correct option. Single option correct, so only 3 options are wrong. The one option is correct. So but first let's study the options itself, because that will give us an idea, that will give us a better understanding of this common emitter amplifier circuit. So first, option A talks about the output is taken from the emitter. So this means usually in any amplifier, this is an amplifier, there is an input side and there is an output side. On BJT we have 3 terminals. Okay, this is usually collector, emitter and base. So which one is the input, which one is the output? That's the question over here. That's the first option that is asking. Second is asking, there is a 180-degree phase shift between input and output voltages. So what this amplifier does is amplifies some voltage, right? We'll see in a while. So let's say the input voltage is like, let's say small, and the output voltage would be big, the swing would be big, right? Let's say this is 1 millivolts. Maybe this will increase it to 1 volts, this values. So it may increase, but there may be a phase shift. So there may be phase shifted by 90 degrees, 0 degree or 180 degrees. What is it? Is there any phase shift? And if it's a phase shift, is it 180 degree or 0 degrees? So that's the option B and C. And the fourth option is PN junctions forward bias. You know that in common base emitter, so this is an NPN. So this is N, collector is N, base is P, emitter is again N. So it asks which one of these junctions is forward biased, which one is reverse biased. Again we'll see in a bit, but these are some very not just common emitter amplifier, for any circuit of BJT, at least the first point and fourth point are very important. Fourth point in fact is the most important. That will determine that how a BJT is, how that specific BJT is behaving. It depends critically on the biasing of the collector, base junction or base emitter and other junctions. So we'll see that in a minute, right? So let's first quickly see what a transistor does. So bipolar junction transistor is made up of 3 words. Third word which we'll talk about first, transistor. A transistor is a device where third terminal is controlling the flow between the other 2 terminals. So as you can see that on the left there's some water. This blue is the water level, and this is a tube. On the right side there's again a tube of the same diameter. So there's nothing connected in between. However, if I were to connect using a straight rod, right, the water will start to flow from left to right? But now I'm creating this weird like zigzag shaped rod. So what's going to happen is that since the water level is just above the level over here, some water will start to flow and you can collect some of this. So this is, you can say this is the supply side, this is the this is where we are collecting the water, this is from where we are supplying the water. So you can see some amount of water can flow. Now now the question is, is there any way that we can lower this barrier or increase this barrier? Let's say if we are lowering this barrier, you can clearly see that on the left side the water level remains the same. However, now more amount of water can flow, right? If I lower this barrier, this is the middle part is the barrier, the left part is the supply, the right part is where we collect the water. However, if I were to artificially raise the barrier, this is the same, the pipe dimensions, the water level exactly remains the same. How if I raise the barrier, you can see this middle part, now it's above the water level, so clearly no water can flow. So what's happening is that just by changing the height of the middle barrier, I'm able to control that how much water is flowing, or if the water is flowing or not. That's what a transistor does. So transistor, by controlling the middle level, it can control the flow of electrons from one terminal to the other. Why it's the junction word here denotes that we are talking about the p-n junctions over here. We'll see that in the next slide. And bipolar means the current is due to both electrons as well as bipolar. Bi means two, polar means poles. So there one pole is electron, the other is holes. So the current is due to both electrons as well as holes, right? So based on how you arrange your p-n junctions, you can be either it can be NPN BJT or PNP BJT. If it's an NPN BJT, an electron is the majority charge carrier. However, and hole is the minority charge carrier. On the other case, in PNP BJTs, hole is the majority charge carrier, electron is the minority charge carrier. We'll restrict ourselves to the discussion on NPN BJT. That's the more commonly used one, right? So these are the schematics. So you can see this is the symbol of NPN BJT. So clearly you can see the difference, that arrow is pointing outwards in emitter. This denotes its NPN. In PNP, the arrow points inwards from emitter to base. This is a PNP, and you can see it's N plus PNN. So this emitter is N, base is P, collector is N, and the opposite side over here you can see the corresponding currents. And this is an important thing, that with questions can be asked regarding this. Usually emitter is high doped, base is very low doped, collector is moderately doped, and the emitter is moderate width, collector is wide because it needs to collect all the electrons, base is narrow because we don't want to lose any electrons that are traversing the NPN junction, because electrons has to travel from this direction to this direction, right? Now that we have seen some basics of a BJT, one of its primary application is this common emitter amplifier. So you can see that what do we mean by common emitter? Common emitter, I am emitting common emitter means emitter has to be common, or in other words you can say you can ground the emitter and you apply the input on the base side. So base emitter junction, you apply the input. You can see there's an input, this is the DC input VBB, and there is an AC input, you can see over here. This is the symbol for AC signal. Similarly, the other junction is collector emitter junction, because emitter is common to both the inputs. I told you that an amplifier looks something like this, right? This is the input side and this is the output side. This is the output side and this is the input side. So on the input side we have emitter and base. So from here we are providing input and we're measuring the output on collector and emitter, right? So emitter is the common to both. The input is being applied to the base and the output is being measured. You can see this is the output voltage. Output is being measured from somewhere over here. Emitter remains the reference. Again, you have a collector biasing, and obviously we are measuring this small thing, the AC V out signal over here. So you can see it's amplified because you apply small input signal IB, but to get a large output IC, because you know that beta equal to IC upon IB. Beta is the current gain. So based on that you can get even though you apply a very small signal, let's say 1 millivolts, you can get, maybe if beta is 100, you can get a 100 milliamp signal for the collector current. Now what I'll try to do is I'll try to break it into two parts, the DC part and the AC part. So let's first discuss the DC part, because it's only this analysis it will determine whether it will even behave as an amplifier or not. So you can see on your screens that this is the output waveform. So this is also known as the output waveform of a BJT. On the y-axis you have the collector current IC. On the x-axis you have the collector emitter voltage. We saw in the last slide, that's where we are measuring the output. You can see that, right? So the first of all, you can clearly see that this orangish region called the cutoff region. In this, base emitter is reverse biased and base collector is reverse bias. Means emitter cannot the emitter cannot provide any electrons, so there is no point of any current being available at the collector. So just to make it more clear, so what's happening is that, so this is emitter, this is base, and this is electrons have to travel from this side to this side, right? So if this is not forward bias, the electrons cannot even transit this region. So this has, so at least, so in the, that's why this you see cut off this very low current. However, when the base emitter is forward bias, you can see in these two cases, so when base emitter is forward bias, and if we reverse bias the base collector junction, so what's going to happen is that there will be a depletion region. These are some in-depth things which you can refer to some NPTEL videos on that. So what's going to happen is that electrons are going to be swept away due to the large electric field. So this is the most common, the middle, between the B and C, this central region that you see, this is where we usually operate an amplifier. And in this, the base collector is reverse biased. Pardon, the base, so this is the condition that we're interested in. Base emitter is forward biased because you want to supply as many electrons as possible. Base collector is reverse biased because you want to collect as many electrons at the collector junction as possible. So this is the configuration in which we operate in. So one is forward bias, the other is reverse bias, and this is the region, the central region that you see over here. This is the active region. On the left you have the saturation region where the base emitter is forward bias and base collector is also forward bias. This is usually used for switching applications, not amplifier applications. BC, this central region, is where we use for amplifier applications, right? So so this is a typical, this is the diagram again in the last slide. So I have just clipped it, a certain part of it. So what I want you to see, what I want to do is I want to apply KVL over here. Follow this line, okay? I'm going to write KVL along this loop. So I can write V plus minus, let's assume IC current is flowing over in this, minus ICRC minus VCE equal to 0. This potential is nothing but VCE. Now VCE is nothing but our x-axis, you can see over here. So I write is at x. V plus is a constant, minus IC is my y, YRC equal to 0. I'll rearrange the terms. We can get y equal to 1 by RC times x plus sorry, it's going to be minus plus V plus by RC. So y equal to mx plus c, you can see that form over here. Excuse me. Yeah, we will get to the answer in a minute, but I want to just explain the concept of BJT. Yeah, so y equal to minus 1 by RC into x plus, so you can see y equal to mx plus c. The slope is negative, right? So what I'll do is that I can draw this line, right? I can draw this line and I can just obtain all the, so you can obtain the intercepts by putting the value y equal to 0. This V plus is nothing but VCC, so this V plus is also referred to as VCC sometimes. So this is what is called a load line, right? So V out is going to be determined by the intersection of this load line and the region over here, right? So let's say I'm interested in this point, the intersection over here. So what I'll do is that I'll apply my bias, we saw in the last, like VBB and VCC accordingly, that our drain current comes out to be this much, and our base current, sorry, the collector current and base current will be IB2, and correspondingly the collector current will be beta times IB2. So biasing is important. We want to bias it near the center, not near the edge, because we want the swing, the output swing. Right, now come to the AC. Once we have biased this circuit, now we want to analyze how does this circuit behave when we apply a small signal, or this is sometimes called the AC signal, right? So this is a corresponding model of AC small signal for this NP and BJT. It's like that, and this was a circuit that we saw 2 slides back. What I'll simply do is that I'll replace the BJT with this model. Secondly, I'll remove I'll short all the independent voltage sources. So you can see I've replaced this BJT with this circuit over here, and I've shorted all the independent voltage sources. If there are current sources, we will open them. Now what I'll do is that I'll simply now analyze this. So we can simply assume it to be ground. I told you this is the reference. right? And now I'm interested in finding the voltage gain. So gain is equal to what? This is going to be V out over V in. So I'm interested in finding what is this value, right? So we know that V out we are taking from here, and this is the V in, right? So if you see, if I apply Ohm's law across this resistor, so Ohm's law across R pi, what will I get? I'll get V, that is V in minus 0. You see, one end is V in, the other is 0. I'll get V in minus 0 equal to current that is IB times R, that is R pi. So I'll get V in equal to IB times R pi. Now similarly, what I'll do, I'll apply Ohm's law across this RC resistor. So Ohm's law across RC. Sometimes this is also known as the load resistor. So these are interchangeably used. So that's why. So this is going to be, so IC is flowing over here. So this current would again be IC. So I can write the voltage across this would be V out minus 0. This is equal to minus IC times RC. This will give me V out equal to minus IC RC. Now V out by V in, gain V out by V in. V out is this minus IC RC, and V in is IB RB. And I know this is a BJT operating in the active region. So IC would be beta IB. So I can write as minus beta RC upon, sorry, this is R pi upon R pi. So I get gain equal to minus beta RC upon R pi. What does this mean? Beta is a positive quantity, RC is a positive quantity, R pi is a negative quantity. This means V out is, this minus sign denotes that V out and V in are 180 degrees out of phase. If the sign were positive here, that means they were completely in phase. 180 degrees means you are completely opposite, diametrically opposite. Hence V out and V in are out of phase. Now we'll come back to our problem. So we saw that output is taken from emitter. No, we saw that input was base, output was collector. So first option is wrong. Second option says there is a 180 degree phase shift between input and output voltage. That is correct. We saw we derived the expression for gain. So we saw that it's coming out to minus beta RC upon R pi, something like that, gain. So input and output voltages were 180 degree out of phase. So this is correct. This is not correct. Both PN junctions are forward bias. No, we saw that base emitter was forward and collector base was reverse, and this mode is also known as the forward active mode, forward active region of a BJT. So this is what we have talked. So D is also wrong. So only option B is correct. Note that this is a common emitter amplifier circuit. There are other configurations like common base or common collector. So the analysis will change in that. But the way I have discussed it, like you first know some basic understanding of BJT, and then you try to find the biasing, the DC biasing, and accordingly then you solve the you draw the AC equivalent to find the expression for gain. So these are the steps if you follow. The question can just be about the gain itself, that find the gain. So that will be a subset of this question. So I just wanted to give you a complete picture because it's a good question that this touches upon all the concepts of an amplifier based on BJT. Similarly, there are amplifiers based on FET, field effect transistors, like MOSFETs. So the analysis remains the same. Very few things change. So that completes this question. But again, I'll pause for a bit, and if you have any part that you want me to explain, again, please ask. I'll wait for a bit.
This question clear, sir.
Sorry?
This clear, sir.
Okay. Mandlik, you okay? If you are there.
Yes, sir.
Okay. So if you're good with that, now I'll move to the next question. This question, how should I say this? This is a question from 2011. A similar question just they changed just this voltage. The same question was repeated, I think 6 or 7 years later. So that's why previous year questions are important. So you must solve all the previous year questions. The GATE exam is 10 days away. Try to solve all the previous year questions if you've not already done so, not just for GATE, for NET and for JEST also, because usually the questions, the statements, they just change the some numerical values or some very just a couple of words, and if you have solved those questions in your room, it's high chances that you can do it in the exam itself. All right, coming back to this question now. Question says, in the following circuit, TR1 and TR2 are identical transistors. We'll see what do we mean by identical. Having VBE equal to 0.7 volts. So we are given that their base emitter is 0.7. This means base emitter is forward bias. Note that these are NPN. So if this is positive, this means this is forward. So base is P, emitter is N. So P is at a higher potential as compared to N. This means this is a forward bias. So BE is forward bias, and the current passing through transistor 2 is, so we need to find this current. Let's call this IC2 maybe. Okay, so we need to find the value for this. Okay, now whenever a question for BJT comes, now you have to make sure in which region are they operating in. Just a few minutes ago we talked about the 4 regions, right? These are the 4 regions that we had talked about. So I told you, when in this region, the between B and C, this is this region. When base emitter is forward, in question it's given the base emitter is forward bias, right? And this is also where you saw the amplifier, but the base collector here is reverse biased, right? So we need to identify first of all whether our transistor is operating in which of these modes, which of these regions. Okay, so we know that base emitter is forward bias, it's been given to us, so it's one of these two, right? But is it, what about the base collector? Is it reverse bias or is it forward bias? Let's try to identify that quickly. So we know that, let's assume this to be 0 volts. This is the first transistor. Let's first talk about the first transistor itself. This is 0 volts, and we are given this is 0.7 volts, right? VBE was 0.7. This is the short. This will also be 0.7 volts. I'm drawing this from here. You can see that this is the configuration for transistor 1. This is transistor 2. So I just copied them over here. So VC will also be at 0.7 volts, and VE is 0. So this means VCE is 0.7 volts for transistor 1. VCE1 is 0.7 volts, and we know that we need to identify between the base collector biasing. So base collector biasing, you can see these are shorted, right? They're neither reverse not forward for this transistor. This means you are exactly at this point B. This is also, by the way, known as knee, because you can see that this is shaped like a knee, this curve. So this is neither in active nor in saturation, transistor 1. But for the sake of simplicity, we can assume it to be in the active region because it's at the junction of it. We can assume it to be anywhere. For the sake of simplicity, we assume it to be in the active region over here. Let's talk about transistor 2. So transistor 2, again this is 0, and we are given it's 0.7 volts. VB is 0.7, but we don't know what this voltage is. If we go back, you can see that this point is corrected to plus 5 volts, right? So this is plus 5 volts. So I can see that VCB2, this is going to be 5 minus 0.7. This is 4.3 volts. Now this is N, this is P. You can see that the N terminal, the collector terminal, which is N type, is at a higher potential as compared to the P terminal, the base. This means this is reverse bias. N is at a higher potential as compared to P. So this means transistor 2 is over here. Base collector is reverse bias. This means we can clearly say that transistor 2 is operating somewhere over here, right? In this region between B and C, this whole region. So we know that now. So I'll write it over here. So we know that transistor 2 is in forward active. We have determined that just now in the last slide. This was at the junction of forward active and saturation, but we can assume it to be forward active without, we are not losing any information by saying otherwise, right? And this is our typical NPN transistor works. So you apply some bias. This is a forward active, by the way. You can clearly see that that collector base is reverse bias. Collector is at higher potential, base is at lower. Similarly, base emitter is forward bias, base is at higher, and emitter is at lower, and these are the dopings. So some electrons will flow, some of a very small amount will get recombined over here, but most of them will reach the collector, and that's how the current will flow, right? And these are the expressions that we saw. KCL will give you I equal to IC plus IB. Beta is the current gain IC upon IB. Alpha is your efficiency, which is given by the collector current, I mean the current which is reaching the output, versus the current at the emitter. So usually this will always be less than 1. For good devices, or for decent biasing, this will be very close to 1, maybe 0.999, 0.995, something like that. And beta typically is 100, 200, something like that. And this is just a KCL. Okay, so now we are equipped with some mathematical expressions, and now we can attempt to solve this problem. This is the circuit that was given to us, and now what I have done is I have labeled some voltages. So I have assumed emitter to be the ground, and you can see in blue, this is VB1, the base voltage for first transistor. Similarly, base voltage for second transistor, VB2, and this is VC1, the collector voltage, the collector voltage for first transistor. Okay, and these are the currents that are flowing. So IC2 is the one that we need to determine, and I is the current flowing through this 100 ohm resistor, and IB2 is the current that will be flowing through the base of transistor 2. Similarly, IB1 will be the current that will be flowing through the base of transistor 1. It will come like this, and IC1 is through the collector current of transistor 1. Okay, and VBE is given at 0.7 volts, beg your pardon, and IC2 is the one that we need to determine. Now, how do we go ahead by solving it? So what I'll try to do is that you can see on this junction, what I'll do is I'll apply KCL at node VC1, at this node. What I'll write is I'll write all the incoming current. So incoming, I'll write this incoming current equal to outgoing current. So incoming current is nothing but capital I. Outgoing current is IB1 plus IC1 plus IB2. You can see these three currents, right? Okay, now remember the question said these transistors are identical. What that mean? If their base emitter voltage is same, their IB will also be the same. IB1 will be equal to IE2, because VBE1 equal to VBE2. Also, beta 1 will be equal to beta 2, because they are identical. Okay, so what I'll do is that I'll simply write this as IB, and if so beta 1 equal to beta 2, so I can write this now as beta IB plus this will also be IB. So I will be equal to beta plus 2 IB. Okay, this is the value of current I that I have obtained. Now, if I apply Ohm's law across this resistor, the 100 ohm resistor, I can write, so I'll write this over here, Ohm's law across 100 ohm. I'll write V, that is 5 volts, minus VC1 equal to I times 100 ohms. So what I'll get is 5 minus, now what's the value of VC1? Note this is 0, and we were given VB equal to 0.7, so this node is at 0.7 volts, right? And this is the same node as this, so VC1 will also be 0.7 equal to I times 100. This will give me I equal to 4.3 over 100. This will be 1043 milliamps. So I get I equal to 43 milliamps, right? So if I put this over here, I can get beta plus 2 IB equal to 43 milliamps. This is the expression that we have obtained. Now I'll come to this. We were required to find IC2. IC2 is nothing but beta IB2, which is nothing but beta IB, right? If beta is large, that means beta is greater than 1, let's say. So beta plus 2 I can approximate as beta. If beta is 100, so we can neglect 2, that's the whole point. So beta plus 2 is approximately equal to beta. Just a second. all right. Beta plus 2 will be approximately equal to beta. So we can say that beta IB, this implies beta IB will be nothing but 43 milliamps, and this is nothing but the value of, we can put this beta IB over here, this is nothing but 43 milliamps. So this is IC2. So IC2 will come out to be 43 milliamps. Coincidentally, IC1 will also come out to be 43 milliamps if we assume beta is greater than 1. You can see that the current flowing through this transistor, first transistor, is exactly the same as second transistor. This type of circuit is also called as a current mirror. In the first question that we talked about, the capacitor one, it was talking about a constant current source. That's how a constant current source is usually produced. So this transistor will always have 43 milliamps, and this will force that current through this transistor to be again 43 milliamps, and you can put one more transistor that will also be 43 milliamps. So that's how a constant current source is usually produced. And note that how this 43 milliamps came, it depended only on this power supply and on this resistor, right? And all these transistors were identical, that was given. So that's why I was telling that there is usually a power supply which drives all these circuits, and that will set some saturation point. So capacitor cannot keep on getting charged indefinitely. So that's what I was talking about over there. But yeah, for this problem we saw that the current through these two transistors will be the same, because this is a mirroring circuit, also known as usually called the current mirror, and the current usually depends only on the voltage supply and the biasing resistor, which is called usually over here. So what we had obtained was that IC2 was 43 milliamps, which is option D that we can see over there, right? So yeah, that's it for this problem. I'll again pause for a bit. If there are any doubts, you can, or any clarifications that you have, please feel free to ask. This is a question I
will you please show that
which part, Pandlik?
that solution bit?
Okay, this was the solution. You want me to repeat something? I can do that.
So beta here we have assumed, right?
Beta, yes, beta, since it was not given in the problem, so you can see that over here. So we obtained 43 milliamps, and this was equal to beta plus 2 IB over here. I cannot get the value of IB unless I know beta, right? But if I assume beta to be very large, let's say 100, 200, what I can do is that I can drop the 2 over here, and I can simply say beta IB is nothing but 43 milliamps. Essentially, I'm saying that base current is, I can neglect base current as compared to the collector current, which is a safe assumption. Yeah, so that's what I'm doing. But usually they provide, if not, you can assume beta to be greater than 1. That's the point.
So can we convert this thing, the circuit diagram which you showed for op-amp?
Sorry.
So the circuit diagram which you showed for op-amp, can we convert this circuit into that?
This circuit cannot be converted, because see, this circuit is what is a current mirror circuit. So these are two different, they both use BJTs, yes, that's true. But so in that circuit, if you remember, I'll write over here, okay? So in that circuit, if you remember, it was something like this. So this was VCC, these were the two resistors, and then we had these two BJTs, right? And then there was a emitter resistor, so this was RE, and the inputs were being, this is over here, two different inputs were being provided. This was what we called V in plus, this is what we called V in minus. If you compare to this circuit, here the inputs are the same, the emitter is same, both the emitters were shorted here also, just like this, but the base, here the bases are at same potential. You can see the base for this transistor and the base for this transistor are shorted. It's not the case here. Here they are usually different, denoted by V in plus and V in minus over there. So it cannot be converted. It uses two BJTs, yes, they are the power supply to their collectors is the same, just like over here it's plus 5 volts. The emitters are shorted just like here, but the base voltages are different. Here the bases are also shorted in current mirror, while for an operational amplifier, or let's say in differential amplifier topography, there the input signals are different. They're not the same. If they are the same, that would mean that that could mean we are in common mode. Yeah. So common mode will look remarkably similar to this circuit, but then see some resistances will play their role, yes, but it functionality would be very close to a current mirror. That much I can say. Not ideal, not exactly close, but you can follow the same process flow as we followed in case of a current mirror. Does that answer your question?
Yes.
Okay. It's not the same. It looks like though, because if you flip transistor 2 for current mirror, it looks like this, but the bases are at a different potential, and hence their functionality is also different. That's a good point you raised though. Okay. Any other comments or questions regarding this?
Clear, sir.
Okay. Now if you have any specific doubts on BJT or electronics in particular, you can ask me, because now I'm going to switch to mathematical physics. I have a couple of questions from the residue theorem that is there, because that's one of the favorite questions that is asked every couple of years maybe, that they give a complex, you have to integrate a complex function over a closed loop, and you are required to find the integral and using the Cauchy residue theorem. So I'm going to switch to mathematical physics. So hence I'm pausing here for a bit, just for your comments, that if you have any regarding electronics in general. So I'll pause, and any questions that you may have, your doubts you may have, or from
Sir,
yeah.
T flip flop and D flip flop.
Okay.
That part can you please explain?
Yeah, I'll do that. Just hold on a second. I'll need to add. Just give me a minute. I'll try to add some space for myself. All right. Is the screen still visible?
Yes, sir.
Okay. So you were asking about D flip flop and T flip flop, right?
Yes, sir.
Okay. So flip flops in general, they are used to how should I say this? They store some value. Okay. So usually in binary they can store a value 0 or a value 1, but that's not useful. You also want to change it depending on your need. Like for instance, when in the night you switch on the light bulb in your room or in your house, right? In the daytime it's not required. Similarly, in summers we switch on the fans or ACs or coolers. In winters usually it's not required. So that functionality is important, that not just it stores it, but it also can update it. So for instance, if 0, you may want to update it to 1. If it's 1, you may want to update it to 0, and it should store that value continuously until you want to update that. So that's the functionality that flip-flops provide. Now there are different flavors of flip-flops. So you asked one of the most common ones. One is the D flip-flop. So we'll talk about this. Is the most common type of flip-flop. Okay. So here is a schematic of a D flip-flop. So what it does is that, so it has one input, usually call it D, and it has the output over here, which I'm calling it Q. This is not the complete picture actually. So often you will see that there is another output called Q bar. Now this is nothing but invert of whatever Q is there. So just you need not bother about this. Okay, for now we'll just assume that it's only D and Q. I want to keep things simple, but you can obtain Q bar just by simply inverting the Q signal. This is the input side. Left side is input, right side is output. I am saying it's the incomplete picture because usually there is one more, and arguably the The critical part of any sequential circuit is the clock. So here you can see this is the clock. This is the clock. So you will provide, so every system will run on a clock. Every computer or system will run on a clock. Usually it's a square pulse, something like this. So you can see I draw it like a rectangular. So this denotes it's an edge triggered circuit. I will not go into this, but just understand there's a clock that is being supplied to this flip flop. Now what this flip flop does is interesting. So I'll write what is called a truth table. So what is a truth table? Truth table is list of all possible inputs and corresponding outputs of a circuit. Note all, this means you have to list every possible combination. So what I'll do, I'll draw this double vertical line and I'll write all the possible input combinations that are there. So there are two inputs I can see. One is D. What I'll do is that I'll write clock on this side, clock and D. So I can write clock as 0, D as 0, clock as 0, D as 1, clock as 1, D as 0, and clock as 1 and D as 1. So no other output, no other combination is possible apart from this. And here is the output which I denote by Q. So when the clock is low, right, the output will be retained. This means, so we call it usually Qn plus 1. This means what's going to happen at the next clock edge. I'll draw a waveform also, but just for the sake of understanding, let's assume this is the Qn plus 1. So what's going to happen, whatever the value of D is, when the clock is 0, when the clock is low, so D flip flop will be switched off. It will not do anything. So the next value of Q will be nothing but the previous value, which is denoted by Qn. Again the clock is off here. D flip flop, it says turn on, but no, the clock is off. D flip flop cannot do anything. It will just retain the previous value, which you denote by Qn. Right. What will happen here when the clock is on? This means the D flip flop can now work. So if the input is 0, the output will also be 0. Right. Since the clock is on here, if the input is 1, the output is 1. Do you know what D stands for? Can you tell me what does this word D stands for? D stands for delay. What's happening is that whatever the input is, you see, when the clock is now, what typically what we consider is we do not even consider this part, because when the clock is off, we know D flip flop is not going to do anything. It's going to just store the values. So we usually you only see bottom two rows in the truth table of D flip flop. So again, I'll also just consider only these two for the time being. So when the input is 0, the output will be 0. However, it will be a delay of 1 clock. What I'll do is now I'll draw the next slide. I'll draw how the output waveform will look like for a D flip flop. So this is my clock, this is my input D. Okay, right. What I want to know, how will Q look like? Okay, so Q, I'm assuming it's only happening at whatever changes will happen will only happen at this edge when clock is rising. So there are many flavors of by the way, a D flip flop. So it can be rising edge, falling edge, many other things, but I'm just telling you a very simplistic picture. So the only thing of interest is what's happening only at this clock edge. So if there are any other changes, I'll ignore that. So when the clock edge is high, sorry, when there's nothing happening, There's nothing happening over here. I'll assume that the initial qn plus q was 0. Initial value was 0. So what's going to happen at this clock edge, now D flip-flop can respond because clock allows it to. So you'll see that the D is 0. So it will happen is that output will change to 0. This means it was 0. Now it will again remain 0. It will remain 0 until the next clock edge. So this will remain 0 until here. Again, this clock now says that D flip-flop can pass its input. So you can see now if D is high, Q will become high. Q now will become 1. Again, when the next edge comes, it will again read the value of D. D is high. So Q will continue till here and Q will continue again high because D is high at this junction. Okay. So this value will be passed on to Q. This will again remain high. Again at this clock edge, it will see that the value of D is 0. So this value of D will be passed to Q. This will remain high till here. This will become 0. What's happening is that Y is called a delay flip-flop or D flip-flop because the value of D is passed on to the out. The value, this is the input by the way. This is the input. This is the output. The value of input is passed to the output with a certain delay. You can see the D became high over here, but the value got passed only after a certain delay, right? Hence it is called a delay flip-flop. Similarly, you can see although the values changed over here, you can see it became 0 and then it became, but that got lost because it happened very fast. So the clock also plays a role. So D flip-flop, the input should not change very frequently if you want to store every value. But the whole point here is that what I want to emphasize is that based on this truth table, the bottom 2 rows especially, when the clock allows, the output will be exactly the same what the input is at that point. So you can see if the input was 0 over here, the output was also 0. If the input was 1 at this clock edge, the output was 1. If the input was 1 at this clock edge, the output was 1. If the input was 0 at this clock edge, the output was 0. And that's how a delay flip-flop or D flip-flop operates. Is it
clear, sir?
Okay. Second one was which one? I forgot.
T flip-flop.
T flip-flop. Do you know what T stands for? Aparna?
No, sir.
T stands for toggle. Do you know what toggle means?
Changes the value 0 to 1
Very
like
good.
that.
Yeah, toggle means it can be from 0 to 1. This is also a toggle, 0 to 1, and from 1 to 0. This means a toggle flip-flop will change the value of output. If the output was 0 initially, it will change it. If the output was 0 initially, it will change it to 1, and vice versa. If the output was 1 initially, it will change to 0. That's the functionality of a toggle flip-flop. How does it look like though? So this is a, so again, this looks something like this. Just hold on a second. T flip-flop. This is the input side. Again, this is the output side. I'm not drawing the Q bar, which is again present. You can always get Q bar just by inverting the Q. So I'm not drawing here. And also there is a clock over here. Okay, there's a clock that's coming to this T flip-flop. Rectangular clock, square pulse that I'm assuming over here. What I'll do again, I'll write the truth table. As you know, truth table is a combination of all possible inputs. So what I'll do is that this is T. Oh, sorry, this is clock first of all. And then there is T, and the output would be Q. Okay. So again, when the clock is 0 and toggle can be 0 or 1, and the clock is high, again the toggle can be 0 or 1. So I told you when the clock is low, so this is the next output. So it will retain the output because the clock is low. So no action will happen even though you are trying to tell this flip-flop to change the values. It will not do because clock is not there. However, when the clock is high, if toggle is 0, this means it will not toggle. Clock is saying you can toggle, but toggle input is saying no, not yet, please wait. So the next output will be the same as the future output will be the same as the previous output. However, if the toggle is high, if T is 1 and clock is also 1, then it will toggle and denote toggle by Q and bar. So the next output will be inversion of whatever the previous output was. Again, I'll try to explain this using a waveform for better understanding what I mean. So this is my clock. Again, I'm taking only rising edge, so you can, this is for the sake of simplicity, I don't want to confuse too much, right? And the next thing is toggle flip-flop, which we denote the input by T. So what I'm going to do is yeah, let's draw some random so let's do this. Okay, so this is the output Q, right? And we are interested only at these edges, because that's where the action will happen. The clock only will allow the output to change only at the dotted lines, only at these time intervals. So again, I'll assume that initially the output was 0. Initially the output was 0. Usually this is provided in the problem itself, right? So here the clock is allowing, but toggle is 0, so no toggle will happen. This means toggle input is 0, so if the initial input was 0, so the final output will also continue to be 0, right? What happens in next event? So when this happens, the clock is saying you can change, and we'll see that toggle input is high. This means whatever the input is, so initial input was 0, now final output will become 1. Sorry, and since toggle input is high, clock is allowing the toggle input to dictate the output. So the output will toggle from 0 to 1, and it will continue to be 1 until the next event. So next event will happen at this time interval denoted by the dashed line. The clock is allowing. Now again the toggle input is high. This means if the toggle input is high, the output will toggle again. You can see if T is 1 and clock is 1, next Q will be Qn bar. So 1 bar is 0. This means it will toggle again. It will go to 0. It will continue to be 0 until this point. Again, the clock is saying toggle input can change the output. But since toggle input is 0, output will not change. Output will remain 0, because you see when T equal to 0, clock equal to 1, the next output is same as the previous output. So 0 will remain 0. Finally, over here, what's going to happen is clock is saying that the output can change, and toggle input is high. So again this will toggle. It will again toggle from 0 to 1, 0 to 1. So that's how a toggle flip-flop behaves. Okay, this is the truth table. Again, as I told earlier, that usually what you see is only the bottom 2 rows. Only these 2 rows you see. These 2 rows are usually not talked about, because clock is low, so no change can happen. So this is only the change is what we want to capture. So changes are happening only at this junction. Okay, so that is okay. So that is the complete picture. But just one more thing. The T flip flop is nothing but a version of JK flip flop. Okay. If
bottom 2 rows are taken. Then first 2 rows are not taken.
Usually, because you see the output is not changing, right? If the clock is not there, the output is not, even though you change the toggle input, if the clock is not there, the output will not change. It will retain whatever the value is. Usually that's not in truth table. Ideally this should be included, but for the sake of simplicity, so as to not to complicate for better understanding, these are usually omitted. But it's not like they're not there. They're there. Functionality wise they are there. For understanding, for teaching purposes, usually sometimes they're not written. That's what I meant to say, but they are happening.
Okay, sir, clear.
Yeah. Okay, so that was that. JK flip-flop, you can, forgetting how to get a T flip-flop from a JK flip-flop, I think you just short the 2 inputs, I think, and then you get a T flip-flop, a toggle flip-flop, by just shorting the 2, I think. Yeah, so if you short J and K, so you can get toggle flip-flop from J and K. I think it's something like this. So this is JK flip-flop has 2 inputs, J and K, right? And then again Q, and then there's again a Q bar which I'm not drawing. Obviously there is a clock which is like this, and if you short J and K, if I'm not wrong, that is, then this is equivalent to nothing but a, you call this T, and this is nothing but a T flip-flop. This is the clock, this is the Q. So this is the same equivalent circuit like this. I'll just confirm, just hold on a minute. I'll just confirm whether this is correct or not, because I don't want to. Yeah, I think this is correct. Yeah.
Okay.
Yeah.
Sir.
All right. So that's about flip-flops. Any other doubts you have?
Clear, sir.
Okay. All right. So if nothing in electronics, then I'll move on to the mathematical physics portion. I have a couple of questions in that. So this is the question that I was in 2012, and I have one more question from 2014. These keep on repeating, so that's why I'm emphasizing. The value of the question is the value of integral C is the contour which is given like this, of a circle with unit radius z equal to 1, and this is the expression that we want to integrate. This is a multiple choice question with one correct answer, and we'll try to find out the correct option. Okay, so this is the problem. This is the integral that is given to us, and we need to find its value, right? And over this contour, C is this contour that you can see, mod z equal to 1. This is the complex plane I have drawn, x-axis and y-axis. Y is imaginary, obviously. So the way we try to find is that, so there's something called the residue theorem. Residue theorem. It says that the integral of a function over any closed loop is equal to 2 pi I sigma residues. So we try to find something called a residue. Why sigma? Because there may be many points. So z equal to zi, so residues at zi. So we try to find the residues at these specific points called zi's. How do we determine which are the zi's? So zi's are usually what are referred to as the poles, where this, note that e raised to the power 1 by z is usually a well-behaving function. So exponential functions are well-behaving, except only at z equal to 0. You see, if you put z equal to 0, this will blow up, e raised to the infinity. This will no more be an analytic function. So what we need to do, we try to find out the residues at the poles. So if we consider this as to be the fz, I'll try to find out the poles for this. So I can write e to the power x can be expanded as 1 over fx plus, I think, x square by 2 factorial. So 1 by z square by 2 factorial, and so on. And you will see the following, the other terms, the higher order terms. So you can clearly see that it will be like 1 over 1 plus z plus 1 over 2z square, and so on and so forth. So z equal to 0, you can clearly see is a pole over here, right? So how do we find the residue? There are many ways of finding the residue, by the way, for such a problem. One of the most common way to find out is to write the expansion of the function. And try to find the coefficient of 1 over z. So here the pole is z equal to 0. So I'll write that. So first step is identify the poles. There can be multiple poles, by the way. So identify the poles. Second step is write the expansion of the function, right? And third step is expansion of function around pole. This is important, around the pole. So here the pole was at z equal to 0, and we write the expansion around z equal to 0, and we find the coefficient of 1 over z minus z naught. So here z naught is the pole, so z naught equal to 0. So we find the residual coefficient 1 over z minus z naught. So in our case, now I'll write this over here. So in our case, z naught is 0 because that's our pole, right? So if you write the expansion around the pole, it will be 1 over z plus something over z square. I forgot the coefficient, and then higher order terms. So we found, now we wrote the expansion. Now finally we try to find the coefficient of 1 over z minus z naught term. So 1 over 1 minus, so coefficient of 1 over z minus z naught, 1 over z minus 0. So coefficient of 1 over z is nothing but 1. So this means the residue at z equal to 0 is coming out to be 1. And note that there is only one pole. This is a higher order pole, but there is only one pole. So the coefficient is coming out to be 1. And we saw that this integral over the contour. Okay, one more thing. The contour has to include the pole. Only those poles we'll consider. So we find out the pole is here, over here, z equal to 0. So we'll only consider those poles which are inside this contour, right? So there is only one pole inside the contour, which is z equal to 0. So identify the poles inside the contour. So this is the complete picture. Identify the poles inside the contour. So contour was mod z equal to 1. So this z equal to 0 falls inside this contour. So z not equal to 0, that's the pole. We wrote the expansion, which is like this. And if I found the coefficient of 1 over z minus z naught, so which was 1. So residue, this is nothing but the residue, this is 1. And this is 2 pi I and sigma residue. So there is only one pole, so sigma will just be only 1. This will come out to be 2 pi into I, and this is the expression. This is the, sorry, the option that is the correct one, which be D, 2 pi I. This is the expression. This is the expression that you must remember. This is that comes from the residue theorem. An interesting thing, I'll just are there any doubts regarding the problem? Because I want to build up on this, because there are many closely associated concepts with just this theorem. This is very straightforward problems which are asked frequently in GATE, maybe in NET and JEST also. Yeah, go ahead. You raise your hand.
Sir, in all exponential cases, we expand by Taylor's theorem.
Yes, because we the reason we do that is because we know already the expansion of the exponential functions. Even for, let's say, sinusoidal functions, right? We know the expansion for the Taylor expansion for a sinusoid, right? Sin z, let's say, if it's given in the problem. So we know the expansion for sinusoid, so we can use that. Because we know that, that's why we are using it. If we had not known that, for instance, the most common ones are exponential, logarithmic, sinusoidal, all the trigonometric ones, the common ones, sine, cos and tan. So we can directly employ them over here. And that's why I told you there are other ways. For instance, you can also take the limits. That's the other way. That is more helpful in case of let's say polynomial ones, where you have let's say 1 over z square minus 6, or z square minus 3z plus 2, where you have two roots, two poles, for instance. There it's better to use the limit approach for you can also, this is, so I told you there are many ways of finding the residue. So the first way, I'll write this here. So first way, how to find the residues, first way is the Taylor expansion. The second one, which is also commonly used, is the limit. You take the limit of limit z goes to z naught, z minus z naught into fz. This is the residue. So in this you use the I'll write it on the next slide, maybe. Yeah, I'll write it here. So there are two ways to find the residues, two common ways. There are other ways also. So first is the Taylor expansion, and then you find the coefficient, corresponding coefficient that you need. Second one is to find this limit. limit z goes to z naught, z minus z naught fz. This will give you the residue. So there are two ways of doing it. So yeah, that's the idea that we try to follow here.
Clear, sir.
Okay. Right. So now what I'll try to do is using the same this is again the same question, not same question, a similar question that was asked a couple of 3 years later maybe. The concept remains the same. We need to find the value of this integral that is given, so I equal to this integral, and over the contour C, where C is a circle given by mod z equal to 4, and we need single option correct question. So we'll try to, this is, I have just rewritten the problem, and so this is what we know for this. Okay, so what's going to happen, so what I'm going to do is right, so we need to find, first of all, as I told you, there are, the first thing is you need to identify the poles. Identify the poles inside the contour. So let's try to do that. So you can, so this is the function that is given to us. Fz is given as z square over e to the power z plus 1. Now z square does not have any poles. It has zeros, but it does not have any poles. The denominator, however, e to the power z plus 1 equal, so when e to the power z plus 1 will go to 0, then the whole function will have some poles. So I'll write that, and e to the power z1 equal to 0. So this will give me the poles. So whatever the value of z that we obtain over here will give us some poles. So let's try to solve this. This will e to the power z equal to minus 1, right? So this would mean I can say z equal to, so this will be minus 1 when it's cos pi. So cos pi would be, okay, so when z is iota times pi, but odd values. Okay, so it will be like this. I'll tell you how I obtained this. So z equal to I pi 2k plus 1. So for the sake of simplicity, let's just assume k equal to 0. Right, so there will be many poles, not just one pole, there will be many poles. So for assume, let's say k equal to 0, so first pole I can write as z0 equal to I pi. Okay, so let's try to find the value of I pi, I into pi, and let's try to find the expression for the denominator e to the power z plus 1. So I'll write e to the power I pi plus 1. Okay, so e to the power I pi, you can so this will be, you know, e to the power I theta is cos theta plus iota sin theta. So this will be cos pi plus iota sin pi plus 1. Sin pi is 0, cos pi is minus 1. So minus 1 plus 1 come out to be 0. And so you can clearly see, so all the when the multiple of pi is odd, then cos pi will turn minus 1, and then minus 1 and plus 1 will give 0. So that's why I wrote only, so k is an integer. So where k is integer, so only odd multiples of pi, so I pi, 3i pi, 5i pi, and similarly on the negative side, minus I pi, minus 3i pi, minus 5i pi, only those will be the poles. So I identified the poles. These are the poles. Okay, these are the poles that I have identified. Now, but that's not the complete picture. We need to identify the poles that are inside the contour. So what I'll do, I'll write just some of the poles, the value of some of the poles. So it will be minus iota 5 pi, minus iota 3 pi, minus iota pi, iota pi, iota 3 pi, iota 5 pi, and so on. And similarly on the negative side also. Note that we are interested only in contour up to z equal to 4. Okay, so what I'll try to do, now write their magnitudes correspondingly. So this will be minus iota will be nothing, this will be nothing but 5 pi, this will be 3 pi, pi, 3 pi, and 5 pi. pi is approximately 3.14. so this means this value will come out to be maybe, sorry, this is minus, no, this is, yeah, on the negative side. So this may be somewhere on this, like these points will be here. So this will be 3.14, this will be around 9 point something, this will be around 10. So this will be minus iota pi, this will be minus 3 iota pi, minus 5 iota pi, and again this will be iota pi, here it will be 3 iota pi. So we can clearly see that only two poles, there are infinite number of poles by the way for this function, for this fz, but we are interested only in the poles that are inside the contour. Okay, so we can see that only these poles are there that are inside the contour. So we are only interested in two poles. So I can write that as z1 as plus iota pi, and let's say z2 as minus iota pi. So I'm only interested as to what's happening on these two poles, and I'm not interested in happening at any other pole that is there. Okay, so these are the two poles of interest to us, right? So this is the first step, and the second step that we try to do is that now what we can try to do is we'll have to expand this function. If I want to use the Taylor series, then I have to expand it first around z equal to I pi, then I'll find the coefficient which will give me the residue. And for the second part, again I expand the Taylor series, this time around z equal to minus iota pi, and this will give me another coefficient, and that will be the second residue. I'll do a algebraic sum of those two residues, and then I can multiply 2 pi I to give me to evaluate this expression. Note that this is nothing but 2 pi I sigma residues. Sigma is running over the poles inside this contour, right? I can do that. That would be a tedious exercise. However, in this case, what I would prefer to do is I'll prefer to use the limit approach. Okay, so let's try to do that. So if I use the limit approach, so that will be limit z tends to I pi, this will be z minus I pi times z square over excuse me, yeah, I think so, yes, I think so, but you need to we need to just evaluate this. Yeah, so if we try to evaluate this, how do I do this? So this is 0 by 0 form. What I can do is I can apply the L'Hospital rule. Yes, I forget how do we do that. Just wait for a minute. I'll try to think of how to apply that rule. So let's just try to put it. So this will be 0, and this will also be 0. So z square is the term which I can simply pull out. Z square I can pull out. This is limit z tends to I pi z minus I pi over e to the power z plus 1. Yeah, so I can differentiate the two terms over here that are here. So this will give me 1 over e to the power z, right? And this is z square that will remain. I'll put z value as I pi, so this will be I pi whole square times e to the power I pi. I just differentiated the numerator and denominator using the L'Hospital rule. This will come out to be minus pi square, and this will come out to be e to the power I pi. We just calculated it over there. I think it was, yeah, minus 1. Cos pi, that's minus 1. So this is coming out to be pi square. Now we'll evaluate the second limit, that is z goes to minus I pi. The expression will be z plus I pi into z square over e to the power z plus 1. So again you can just take z square out, again limit z tends to minus I pi. So this is z plus I pi over e to the power z plus 1. Again this is e z square, so differentiate this will become 1. Denominator will remain e to the power z, so this will again become minus I pi whole square over 1 over e to the power minus I pi. This will again this will again minus pi square. This will again be minus 1, so this will also come out to be pi square, right? And we know that this integral will be 2 pi I sum of residues. So we have calculated the residues over here. So this is 2 pi I. First residue is pi square, second residue is also pi square. 2 pi I into 2 pi square, which will come out to be 4 pi cube I. Yeah, you are correct. C is the correct option that we have obtained for this question. Yeah, so that's that. Yeah, just so as I was talking earlier, that there are two approaches of finding the residues. So that's what I was coming to here in the previous question, because the pole was at where was it? Yeah, the pole was at z equal to 0, and so this expression could we already knew that expansion for e to the power 1 by z, and so it was fairly simple just to write this. It was a better approach to write the expansion for the exponential over here rather than going through the limit thing, and we simply could just find the coefficient of 1 over z minus z naught. Z naught was 0, so that was the approach over there. Here, since there are, first of all, in this problem, since there are two poles which we have identified, this is a key thing when exponents, because in complex sometimes this happens that odd multiples or even multiples for trigonometric terms. So this is a fairly common feature, and you have to be careful about it, because if you take only one pole, then the answer will be different. So first we have identified the poles, and mind you, inside the contour first we find out all the poles that are there, and then we tried to find out that which ones of them fall inside the contour. So we could see that only two of them out of the infinite poles were falling inside the contour, and then we tried to find the residue. So but we did not use the Taylor series approach, because what we saw that because then we have to expand it along the these two terms, and we have to write this expression twice, and it will increase your steps, that's all, in time. But what we did was that we went for an alternate approach in this case, which was to find the limits. And then once we wrote the limits, and then this was a 0 by 0 form, you can see if you put z equal to I pi, so 0, and this denominator will also come out to 0 because it was a pole for this, right? And this is a simple pole. That's how we could do it. If there are okay, I should clarify this even further. So a simple pole is a first order pole. What that means is that this is the form of z minus z naught raised to the power 1, where z naught is the pole, right? And there may be other poles, z minus z1 raised to the power 1. So z naught and z1 are simple poles. However, if there is z minus z2 raised to the power 3, let's say, this is not a simple pole, this is a pole of order 3. So for instance, which we saw in the last problem over here, z equal to 0 was not a simple pole. You can see there will be it's 2z square, and there will be 3 factorial z cube. So you see that the z keeps on increasing, and the power of z keeps on increasing. So here z is not a simple pole. So that's a key difference. In this, however, it was a simple pole. However, what shall we do if it's not a simple pole? It's simple. So what we do is that if it's not a simple pole, I'll write this expression here. Limits z equal to z naught, z minus z naught to the power n, and there's also differential term here, sorry, factorial, yeah, and then you try to find this term, whatever the function that you have. So try to evaluate this, okay. and I think there's a differential also. So yeah,
Sir, differential with respect to n, next part.
yeah, in this over here, right?
D by dz to the
Yeah,
power n.
yeah, so that's the form that we take. That's for the case of higher order poles, but for first order, differential term will vanish because we're talking only the first term. So these are the important things, and I again emphasize that thank you for correcting, by the way. I had forgotten about this thing. So these are the things that while we talk about the residue theorem and finding the integrals. So not only this, there are some even more complicated problems can be formed. So for instance, I remember, there's something like you take this contour when you try to evaluate the integral on some real axis, right? So try to see some previous year problems. That's my suggestion. Like you want to find the integral or only on this, but you can use this contour integral to evaluate some expressions which just by doing the real integral analysis you will not be able to do easily. The algebra will be very much complicated there. But if you employ the complex analysis, especially the residue theorem that we have talked about over here, it simplifies things to a great extent. Simplifies, and yeah, so that's the whole idea, and you can evaluate some very complicated integrals also. All right, so that's it about the residue theorem from my side. I'll again pause for a minute or so because we have talked about two different approaches. There are other, I think there is one more I'm not able to recall, but I think there is at least one more approach to find the residues. The Taylor series is also, I think, called the Taylor-Lorentz series, because Taylor series is usually what we see only in the positive powers of Z or X, whatever it is. But for when the powers is in let's say when the power is in negative, like we saw 1 by Z plus 1 by 2 factorial Z square and so on, those are also called the Taylor-Lorentz series, if I am not mistaken. The combined picture is known as that. So it's good to remember some of the common how should I say this, the common expressions, the common expansions. That's really helpful. All right, so that's about the residue theorem. Any comments, any doubts, any questions regarding this?
Clear, sir.
Okay.
Sir, how many more questions?
We are, what's the time? So we are actually out of time. I had one more, but if you have any doubts, then you can ask, because I don't think I'll be able to complete it in 2 minutes. Thank you for your time.
Thank you, sir.
Yeah, best of luck. Goodbye.
Sir,
Yeah.
if I have any doubts, how can I
Okay.
contact?
Sorry, I forgot to mention that.
Mail ID,
So yeah,
if possible.
yeah. Just 1 second. You can it's learnwithamitbansal@gmail.com. You can email me on this and I'll try to reply as soon as possible. I've written in the chat box. Can you see?
Thank you, sir.
Yeah, okay. Welcome. Goodbye. Thank you for your time.